All right, so this is the part 2 of the final review. So we're getting there. So again, like I said, it's probably be pretty handy to have a periodic table with you. Also, I'd probably have the polyatomic list just to have that kind of with you, so I'm not scrolling back and forth. So let's go ahead and get started. One of the first things I'm going to do is I'm just going to touch base on the periodic table and finding charges again, because that's where we see a lot of confusion. And once we get to the naming part, if you don't know how to find a charge on the periodic table, it's going to make your life a little bit difficult. Okay, so I have the periodic table right here. So we're just going to go over how we find the charges on this periodic table. Okay, so remember, we find our charges based on valence electrons. Valence electrons are these little numbers right here. So the 8A, 7A, 6A, 5A, 4A, 3A, 2A, and 1A. Okay, so the perfect number is 8. So we're going to start on this far side. So if I have 8, I don't need anything. So my charge would be 0. Okay, group 7A, they're right there. They're almost at 8, so they're missing 1. So that's why it's going to be a -1 charge, because it's going to gain an electron. Then 6A, it's missing 2, so it's going to gain 2. 5A, it's missing 3. 4A, so this could go either way. So this is a plus or -4. A lot of students ask, when is it going to be positive or negative? It really just depends on what it's bonded with. So if you have a positive, say you have lithium, which is positive, is bonded with carbon, it has to be negative, because positives aren't going to really be attracted to each other. Okay, they actually repel each other. So moving on to the next group, I have group 3A. This is going to be a +3, okay, because they're not going to find 5 electrons. So they're more likely just to give up the 3 that they have, okay, because they're not going to find those 5. So we're going to jump across here to 2A, and this is going to be +2. Okay, they're not going to find 6. They're just going to give up 2. And then lastly, this one's going to be +1, because they're not going to find 7, and then they'll just give up that 1 that they have. Okay, so now in the middle, these are your transition metals. Okay, so it starts at my D group right here, and it's going to go all the way to the staircase. Okay, there are some exceptions though. There are a few exceptions. So I'm going to do that in a different color. Silver is going to be a +1 charge always. Zinc is going to be +2, and aluminum is going to be +3. Okay, everything else in that group, whenever we start doing our naming, that's when we use our Roman numerals. Okay, so if it's transition metal that's not one of those 3, it will need a Roman numeral to tell me what the charge is. Okay, so we'll kind of refer back to that when we start doing the review stuff. So let's jump back to where we left off on the last video. So I believe we left off on number 31. Describe the properties of the following families in the periodic table. Okay, so alkali metals, this is going to be that group 1/1A. So that very first group on the periodic table. Okay, so on our key, it goes pretty in depth. So we're just going to kind of touch base on the key points. They have 1 valence electron. Okay, they are soft and easily cut. Okay, so soft and easily cut. They are very reactive. Okay, so meaning that they want to be with somebody. Okay, so that's why they're never found alone in nature. Okay, so they're very reactive. That means that they want to bond with somebody. So it's not going to be found by itself. And then it can even be so reactive that it is explosively with water. Okay, so that's just kind of the main things. You can look on the key that goes a little more in depth. So B, alkali earth metals, that's going to be that group 2/2A. So right next to it. Okay, so it's going to have 2 valence electrons. Okay, it's still going to be reactive, but not as reactive as group 1. Okay, so it's going to be a little bit shinier, so a little more of a shinier metal. And then it's also going to be a little bit more harder. Okay, so not as soft. Okay, so again, you can look on the key to see if you want to go a little more in depth. I'm just kind of touching the bases. Okay, halogens, we're going to jump all the way across to that second to last group. That is going to be that group 17. Oops, don't know what happened there. 17/7A. Okay, they're going to have 7 valence electrons. Okay, and they're going to be very reactive as well. The reason why is because they have 7 valence electrons. Okay, so they are 1 away from reaching that perfect 8 valence electrons. They're going to be very reactive. They're going to want to try to find an electron from anyone they can get. Okay, then lastly, you got your noble gases. Noble gases is that last one, so that's the group 18/8A. They have 8 valence electrons. Okay, so they are not reactive. Okay, the reason why is because they have their 8 electrons. So they don't really need to be with anybody. Okay, so they're not going to be very reactive to other elements. Okay, and they're going to be all are gases. So that's why they're called the noble gases. Okay, and then most are going to be, oops, don't know, there we go. Most are going to be colorless and odorless. So again, just kind of, you can look over the key for a little bit more in-depth answers. Those are just kind of the key points that we need you to know. Number 32, elements in the same group have the same family, same group and family have the same physical and chemical properties. Why? Is because this right here, there was a question on the last test, same valence electrons. Okay, so if they're in the same group, meaning the same column going up and down, okay, they're going to have the same characteristics because they have the same number of valence electrons. Okay, so if they're not in the same column, the vertical column, they're not going to have the same characteristics. That's why they're called a group or family. Okay, compare and contrast Mendeleev's, Moseley's arrangement of the periodic table. So what you mainly need to know is that Mendeleev, he was the first one, okay, back in the 1800s, and he arranged it by atomic weight. Okay, then in the early 1900s, so he arranged the periodic table by atomic weight. Then in the early 1900s, Moseley came along and he improved it. So he arranged by atomic number. That's mostly the gist of that one. Answer the following radiation EMR questions below. Okay, so first thing we need to do is we need to make sure you know the waves. Okay, so we're going to start with our radio wave. So we have radio. Okay, then it's going to be microwave. Okay, then it's going to be infrared, so IR. Then we have visible light. Then we're going to have UV. Then X-ray. And then lastly, we're going to have gamma. Okay, so you can come up with a saying if you want to. I know some of the classes are using real Martians invade Venus using X-ray guns. So whatever you need to do to kind of help you know that. And then real quick, we can break down our visible colors. Okay, and it sounds like a cowboy's name. It's Roy G. Biv. So Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet. Okay, so radio is going to have the longest wavelength. Okay, so remember wavelength is characterized by the upside down Y. It's going to have short frequency. Okay, very low frequency, and then very low energy. Which makes sense. Radio waves are all around us. So if it had high energy, that would not go too well for us. Like cell phones use microwaves, so if that had high energy, it would not be too good to hold those in your pocket all day. Okay, now versus gamma. Gamma is going to have very short wavelengths and very high frequency and very high energy. You would not want to be around gamma waves. Okay, so list all the forms of EMR, including all the colors of visible light from lowest frequency to highest frequency. So I just listed them all up above. So lowest frequency is going to be my radio, and that means we're going to go this way. Okay, so lowest frequency would be on the left, highest frequency will be on the right. Frequency just means number of waves. Okay, so if I have over here on radio, I have very long chill waves. Okay, so I have long wavelengths and I have very few waves per second. So that's a low frequency. When I go over here to gamma, it's going to be a lot of waves, even smaller than this. Okay, so I'm going to have very short wavelength and very high frequency. So I'm going to have a lot of waves in 1 second. Number 2, shortest wavelength to longest wavelength. So my shortest wavelength would be gamma. That means we would rank it going this way. So you have to really pay attention to how we ask these questions, lowest to highest, shortest to longest. Okay, so you have to pay attention on which way to actually go. B, describe the relationship between energy and frequency. Okay, so this is a direct relationship. Okay, so if energy goes up, frequency goes up. And it's usually because frequency goes up, energy goes up. So the way I kind of explain this is if you ever go to the beach and it's a nice calm day and you have very few waves, okay, so that's low frequency, a low number of waves. You're not going to feel much when you're out there swimming. Okay, now if you try to go out there just after a storm and you have a lot of waves coming in and you try to go out there and swim, okay, you're going to feel all that energy from the ocean, all those waves crashing on you. Okay, so that is a direct relationship. Okay, describe the relationship between wavelength and frequency. So this is an indirect, meaning it's one goes up, the other one has to go down. Okay, so if my wavelength goes up, my frequency has to go down, which makes sense. If I make my waves longer, I can't fit as many in 1 second, which is what frequency is. So if I decrease my wavelength, I can increase my frequency. Okay, so that is an indirect relationship. Okay, so now let's go over here. So this is going to be our equations. Okay, so we're going to give you these constants, and we're going to go over the 3 equations. You have your first one. The way I do this is I spell it like the word C, S-E-E. I just do C with a C. So C-E-E. Okay, so C with a C. So that's kind of a start to kind of help you know where to begin. Okay, let me clean that up a little bit. Okay, first one, C is going to be frequency times wavelength. So C is the speed of light. So that's a wave. So light is just nothing but a wave. And a wave is made up of 2 components, frequency and wavelength. Okay, then you have E equals H times F. H is a constant. Okay, so that's not going to change. So if frequency goes up, energy has to go up. Then lastly, you have E equals H times C over wavelength. Okay, so if I increase my wavelength, that's going to decrease my energy. Okay, so one thing you can do on this one right here, I'm going to put a star by it, is if you were looking for wavelength and they gave you energy, all you have to do is just switch these two. Okay, so that's the same thing as saying wavelength equals H times C over E. Okay, so you can kind of flip-flop those back and forth. Okay, so let's do some problems. A, calculate the frequency of a wave which has a wavelength of 4.15 meters. Okay, so you're going to need a calculator for this. Okay, the way I do this is I label what I'm looking for and I label what I'm given, and that tells me which equation to use. So they want to know frequency, so frequency is my question mark. And they gave me wavelength, which is the upside down Y. Okay, so that's what they gave me. So I'm going to use the equation that has both of those, which would be C equals frequency times wavelength. Okay, so C would be 3.0 times 10 to the 8th. Okay, or 00, sorry, we gave you the 3.00 times 10 to the 8th, equals frequency, I don't know, I'm going to leave it as F, and I know wavelength is 4.15 meters. Okay, so what I'm going to do is I'm just going to divide both sides by 4.15. I will say this, when you're doing these calculations, if you are doing 3.00 times 10 to the 8th, please put this in parentheses. If you're going to do the times 10 with the actual exponent, it makes things a lot easier if you put it all in parentheses. Otherwise, your calculator can get confused and you can get completely wrong answers. Okay, so just put those in parentheses and it'll save you a lot of time. Okay, so we're going to do 3.0 to the 8th power divided by 4.15. Okay, and I get a really big number. Okay, so I'm going to switch my calculator mode to scientific. I'm going to run that again. Okay, and I get 7.228 times 10 to the 7th. I have 3 significant figures right here. I have 3 significant figures right here. So my answer would need to have 3. Okay, so if I have this, so this thing keeps jumping around. 7.228 times 10 to the 7th power. Okay, I would count 1, 2, 3, draw my line. That 8 tells me I'm going to round up. So my answer would be 7.23 times 10 to the 7th. And we're talking about frequency, and the unit for frequency is hertz. Okay, so that would be my answer right there. Okay, let me kind of clean up that box real quick because I got into my other question. B, what is the wavelength of a wave with a frequency of 5.77 times 10 to the 14th? So we are looking for wavelength, and we're given frequency. Okay, so we are going to use that same equation. I'm not going to go through this one since we just did that one. So you're just going to use this same equation, and then you're going to solve for wavelength. Okay, so you're just going to take C and divide it by F, and that equals wavelength. C, what is the energy? So that means E is our question mark, and we know wavelength. Okay, so we're going to use the equation E equals H times C over wavelength. Okay, so we're going to do E. We don't know. I'm going to leave it as E. H is 6.626 times 10 to the negative 34. C is 3.00 times 10 to the 8th. Okay, all over our wavelength, and that is going to be 7.67 times 10 to the negative 7. Okay, so I will say that this is one of those problems that I would recommend keeping everything in parentheses. Otherwise, you can get a really wrong number. Okay, so we're going to do 6.626 to the 34th power, negative 34, times 3 to the 8th power. Then we're going to divide that by 7.67 times 10 to the negative 7. Okay, and I get this right here. I get 2.5916 times 10 to the negative 19. Okay, so I have 4 significant figures right here. I have 3 right here. I have 3 right here. So my answer has to have 3. So I would count 1, 2, 3, draw my line. Okay, and that 1 would tell me I'm not rounding up. So it would be 2.59 times 10 to the negative 19. And we're talking about energy, so that is joules. The unit for energy is going to be joules. Okay, D, an X-ray photon has an energy of 2.99 times 10 to the negative 18, so we know E. And we're looking for wavelength. Okay, so we're going to use that same equation. I'm not going to do this one. I'm going to show you how you get there. So E equals HC over wavelength. Except we're looking for wavelength, so what I would do is switch these two. So wavelength equals H times C over E. So that's all you're going to do is H times C and divide it by E, and there's your answer. E, what is the wavelength of a wave that gives off 5.6 times 10 to the 23rd joules of energy? Okay, so wavelength I don't know. Okay, and I know E. Okay, so that's going to be the same thing. So E equals H times C over wavelength. And I'm looking for wavelength, so I'm going to switch those two. So this would just be wavelength equals H times C over E. Okay. And then, so we're going to jump over here. Let me move this over a little bit. Okay, so on this review, I realized that we didn't have a question over E equals H times F. Okay, so what they would do is they would either give you energy, and then look for frequency, or they're going to look for energy, so that's my question mark, and they would give you frequency. Okay, so if it deals with E and F, you're just going to use the equation E equals H times F. Okay, so that one's a pretty simple one. Okay, so number 36, so now we're going back on to the periodic table. So we're going to kind of scroll down here real quick just to kind of go over this a little bit. So my periodic table, so let me kind of clean this up a little bit. You have three main groups. Okay, so you have metals. Okay, so I'm going to do some different colors here. So metals are basically anything left of the staircase. Okay, so those are going to be metals. So metals make up majority of the periodic table. Then you have metalloids, which are the ones that are touching this staircase. Okay, so right along this line is called metalloids. Okay, so the things that are touching this staircase, so that means they're going to have properties of both metals and nonmetals. Okay, all except for aluminum. Aluminum is just going to be a metal. Then over here, this is where you're going to have nonmetals. Okay, so your nonmetals are going to be to the right side of the staircase. So that's just kind of a little bit on the periodic table of how we kind of break those up. So let's go up, or first let me clear this up a little bit because we're going to come back to this periodic table. Okay, now let's go back up to where we were. Okay, so complete the following table on the metals, nonmetals, and metalloids. Okay, so metals are going to be left of staircase. Okay, nonmetals are going to be, I'm going to switch colors because I don't like that. Nonmetals are going to be right of staircase. And then metalloids are going to be touching the staircase. Okay, so they're touching the staircase except for aluminum. Okay, and then as far as metals, the only thing that's not a metal on the left side would be hydrogen. Okay, so this would be except hydrogen. Okay, because the reason hydrogen is over there is because it has one electron. So that's why it's in that group 1. But hydrogen doesn't really fall into any group. So it's kind of its own thing. Okay, as far as properties, so our key kind of goes a little more in depth, but I'm just going to hit the main points. Okay, so it is going to be, just like metal you would think, more of a shiny luster. Okay, so it has a high melting point. Okay, which makes sense. It takes a lot of heat to melt metal. Okay, good conductors. Okay, so conductors of both heat and electricity. Okay, they're ductile, which means we draw them into wires, which makes sense. There's a lot of electricity, like a lot of electrical wiring and stuff has metals drawn into wires. Okay, and then metals are also going to tend to lose electrons. Okay, so they're the ones that are going to bond with the anions or the nonmetals to give them electrons. Okay, nonmetals, these kind of get all over the place, so they can vary greatly in appearance. Okay, so some can kind of be liquids, some can kind of be gases, things like that. So they can just kind of vary. So it's not as common as metals. Okay, so these are going to be not shiny or lustrous. So not shiny or lustrous, which makes sense. Okay, they have low melting points. Okay, they are poor conductors. Okay, so not very good for heat or electricity. They are not malleable or ductile. Malleable just means the ability basically to bend. Okay, so they're not going to really do much as far as that. So pretty much quite the opposite of metals. And then lastly, they are going to be the ones that gain electrons. Okay, so they're going to usually bond with metals to gain electrons. Then metalloids. So metalloids are the ones that kind of touch the staircase, and so they're going to have characteristics of both. So that means they can be kind of, so mostly they're going to be semiconductors. Okay, so some of them kind of can work with electricity and heat better than others, but they just kind of share characteristics on both sides. So they're just kind of stuck in the middle. Okay, so they're kind of stuck in that limbo. Okay, as far as metals, as far as examples go, you can pretty much just pick anything left of the staircase. Okay, so you can say like gold, okay, silver, barium, basically anything left of that. On the right side, just pick anything to the right side of the staircase for nonmetals, so that can be carbon, oxygen, fluorine, any of those. Okay, and then metalloids are just going to be the ones that are touching that actual staircase, so things like silicone, germanium. Okay, so anything just touching those, except for aluminum. Okay, so now let's go on to atomic radius. Okay, so atomic radius is just simply the size of an atom. So this should be pretty fresh in your mind since we just had a test on this. Okay, so the main thing I want you to know for atomic radius is it is going to increase as you go down to the left. Okay, so as we go across a period, so if we go across a period this way, it's going to decrease. As we go down a group, it is going to increase. Okay, so what causes that? So as we go across, okay, we have more protons, and they pull the electrons in closer. So if I'm pulling something in closer, my size is going to get smaller. As I come down, I'm adding electrons. Okay, so if I'm adding electrons, I'm just going to keep getting bigger and bigger. Okay, so ionization energy. Ionization energy is just the energy. Oops, let me fix that. Just kind of bear with my handwriting here, so I'm trying not to mess with the PDFs on here. So it is just the energy to remove an electron. So energy to remove an electron. So it is going to increase as you go up to the right. I will say you have to really pay attention to these questions on the review, okay, because how we word it, okay, will determine on which way you rank them. So if I was asking you to go from highest energy to lowest energy, you would go from top right to bottom left. Okay, so you have to really pay attention to how those questions are worded. Okay, so as we go across a period, you're going to increase. And as we go down a group, okay, it's going to decrease. Okay, so the reason why is, so as we go across, okay, so we're adding protons, so we're pulling electrons closer. If we're pulling them closer, it's going to be a lot harder to steal. Okay, so as we pull them closer, it's going to take a lot more energy to remove one of those electrons. As we go down, we're adding electrons. Okay, so if we're adding electrons, electrons are further from the positive nucleus. Okay, so as those electrons get further and further away, that nucleus cannot hold on to them as well, so it's going to be a lot easier to take one away, so it's going to take very little energy to remove one of those, remove those away. Okay, so electronegativity, this is just simply the ability to steal. Okay, so the ability to steal an electron. So who needs an electron? Okay, so this is going to increase the same way as ionization energy. So it's going to increase as you go to the top right. Okay, so that means as we go across to the right, it's going to increase. Okay, and then as we go down, it's going to decrease. Okay, so the reason why is as we go across, we have more protons. okay, which are going to pull other electrons towards the atom. Okay, so also you look at, as you go across a period, it is going to, you're going to get closer to those 8 valence electrons. So remember, as you get closer to 8, they're going to want to try to get to the 8. So that's why they're going to steal electrons from other atoms. Then as we go down, okay, so we are adding electrons. Okay, and if we're adding electrons, they're kind of getting in the way. Okay, so that means the positive nucleus is shielded from any of the electrons that are kind of passing by from other atoms. So they cannot pull from another atom because you have too many electrons that are in the way. Okay, so number 42, for the following combinations, draw an electron dot diagram / Lewis structures and show the transfer of electrons. Also write the chemical formula and name. Okay, so you would look on your periodic table and you would see that aluminum has a charge of +3. Oxygen has a charge of -2. Okay, so I can tell right now that these are not balanced. So if you want to do the crisscross method, you can take this 2 over here and take this 3 over here. And so that means I need 2 aluminums and then I need 3 oxygens. Okay, so what I'm going to do is I'm going to go ahead and just write the name of it. Okay, so aluminum. So the cation's name does not change. And aluminum is in that transition group, but remember it's always a +3, so you do not need a Roman numeral. And then oxygen now becomes oxide. Okay, so that anion is the one that changes its name. You just add IDE to the end if it's just the element by itself, if it's just oxygen. Okay, so that means I have 2 aluminums. So I'm going to draw 2 aluminums. And then I'm going to draw 3 oxygens. Okay, so aluminum is going to be in that group 3. So 3A, meaning it has 3 valence electrons. So each one is going to have 3 dots. So 1, 2, 3. And then down here, 1, 2, 3. Oxygen is in that group 6, that 6A, that 16/6A. So it's going to have 6. So 1, 2, 3, 4, 5, 6. 1. I'm going to give myself some more room on this one. Sorry, I'm just going to draw this a little bigger so you can see it. So I have oxygen, oxygen, and oxygen. So I got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So you can see how the oxygens are needing 2 to make that 8. So we're just going to start taking electrons from the aluminum and giving them to the oxygen. So one's going to come over here. Okay, another one's going to come right here. Then I have one going over here, one going over here, and then one here, and then one here. Okay, so you can see now why 3 oxygens would need 2 aluminums to make the perfect 8. Okay, so we'll do another one of these just so you can kind of see. Okay, so let's actually do the transition metal right here. Lead 3 and nitrogen. Okay, so lead 3, so lead is Pb. And that 3 tells me that is the charge of lead. Not how many I have, just the charge. Okay, then I would look on my group for nitrogen. Nitrogen has a -3 charge. Okay, so this is balanced. So you would just draw Pb in. Okay, so that means we're going to go on to our naming now. So we already know Pb is lead. Okay, give me 1 second. I think it kind of jumped ahead. Okay, so bear with me on that. I kind of jumped ahead of y'all. Okay, so Pb plus 3, so this is going to be lead 3. Okay, so since we're still going to keep that 3. And then nitrogen becomes nitride. Now we're going to show what it looks like. So lead is Pb. It has 3 valence electrons, so 1, 2, 3. Okay, nitrogen is going to have 5 valence electrons. Okay, so it's in that group 15/5A. So 1, 2, 3, 4, 5. Okay, so that means these 3 are going to join this nitrogen to make nitrogen perfect 8. Okay, so that is how we kind of draw those Lewis dot structures. Okay, so my mistake, so I kind of jumped ahead. I went from 37 to 42, so I kind of scrolled down. I was wondering why it went straight into that, and so now it kind of makes sense. So we're going to do some examples from the atomic radius, ionization energy, and electronegativity. Okay, so we're going to go back over here to the left. Okay, so largest atomic radius. So if I want to rank it from smallest to largest, that means we're going to go from the top right to the bottom left. Okay, so we have calcium, potassium, and bromine. So I'm going to do a couple of these examples on the actual periodic table. Okay, so give me a second. Let me get my other one. Okay, so I have calcium, which is right here. I have potassium, which is right here. And then I have bromine, which is right here. Okay, so remember, atomic radius is going to rank from top right to bottom left if we're going from smallest to highest. So that means bromine would be the smallest, followed by calcium, and then followed by potassium. Okay, so your correct answer would be Br, Ca, and K. Okay, so I'm going to kind of go over just a few of these examples, and you can kind of check the key to make sure you're right on the other ones. So lowest ionization energy. So remember, ionization energy was the highest at the top right, and then the lowest at the bottom left. So if we're going to go from the lowest high ionization energy, okay, so we're going to rank it from top right to bottom left. Okay, so let's do an example of that one. So let's do the C, Li, and O. Okay, so let me clear this up. Okay, so I have lithium, which is right here. Okay, I have carbon, which is right here. And I have oxygen, which is right here. Okay, so if I'm wanting to go, looks like, so we should start with the lowest and then go to the highest, which would make sense, because back on here, it's talking about going from lowest to highest. Okay, so that was kind of I think my kind of review kind of messed up a little bit there. Okay, so lowest to highest, so we're going to go lowest to highest on all of these. So that's the way I'm just going to kind of look and see what we're doing over on the left. So lowest to highest. So lowest is going to be lithium over here, followed by carbon right here, and then oxygen is going to have the highest ionization energy. Okay, so on my answers, lithium is going to be the smallest, or the lowest energy, followed by carbon, and then followed by oxygen. Okay, electronegativity. So if we're going from lowest to highest, that is going to go up to the right. Lowest to highest, so back on the last one was going up to the right. So let's do an example there. So I have phosphorus, silicon, and sulfur. So let's go back down here. Okay, I have phosphorus, silicon, and sulfur. Okay, if I'm going from lowest to highest, that means it's going to go this way. Okay, so silicon is going to be my lowest, followed by phosphorus, and then sulfur. Okay, so silicon is going to be my lowest, followed by phosphorus, and then sulfur. Okay, so that's just kind of how you do that. So you really just need to know that atomic radius gets bigger as you go down to the left. Okay, so it is the only one that increases as you go from top right to bottom left. Ionization energy and electronegativity both increase as you go from bottom left to top right. So just make sure you watch out for the questions and how they're worded on the test. Okay, number 39. Okay, so you're going to need your periodic table for this. Okay, so we're just going to do a few of these. Okay, give me 1 second. Okay, so I have cesium. You would look up cesium on the periodic table. That is abbreviated CS. It is in group 1/1A. Okay, so remember, group is going up and down. Okay, period is the one that goes from left to right. Valence electrons, so just look at that 1A. That means there is one valence electron. Oxidation number just means charge. Okay, so this is going to be a +1 charge. Okay, ion symbol, so that's just the abbreviation with the charge, so CS with a plus or +1. Okay, this is going to be a cation, okay, because there's a positive charge, and we do not change the names of cations, so this would just be cesium. Okay, so if I did strontium, okay, if I found strontium on the periodic table, so SR is strontium. Okay, it is in group 2A, say 2/2A. Okay, valence electrons, since it's 2A, that's going to be 2 valence electrons. Charge would be a +2. Ion symbol would just be SR with a +2. Okay, it is a cation, so we're not going to change the name. So it's just going to be strontium. Okay, so let's do some actual negative ones. Okay, so if you look at bromine, or Br is bromine. Okay, that is going to be in group 7A, or 17/7A. 7A means 7 valence electrons. Charge will be a -1 because it's missing one. It needs that 1 to make 8. So we're going to do Br with a -1 charge. Okay, that is an anion. And remember, anions are the ones that change their names. Okay, so bromine now becomes bromide. Okay, so let's do another negative one. So oxygen is just O. Okay, that is the group 6A. So that means it's going to have 6 valence electrons. That means it has a charge of -2 since it's missing 2 to make that perfect 8. So you're going to go O with a -2. Okay, this is an anion, so therefore we're going to change the name, and this now becomes oxide. Okay, so you can kind of check the others on the review if you want to practice those. Okay, and then check the key on that. So we're going to jump over here to 40. Okay, so monatomic cation, so mono means 1. Okay, so only one atom. So I'm going to put monatomic, only one atom or element. Okay, so only one atom. So that's what mono means. Okay, so this is going to be a positively charged. So cation is positive. Positively charged atom. Okay, example would be something like Ca +2 or H with a +1. Okay, so that is a monatomic cation. Monatomic anion, so mono still means 1. Okay, but this is going to be a negatively charged atom. Okay, so that could be like something like Cl- or N -3. Okay, so it is just one element by itself. Polyatomic, poly means many. Okay, so you're going to see multiple atoms. Okay, so 2 or more atoms. So this would be like that list. So I have that list down here. We're going to give you these. Okay, so this is the polyatomic ion symbol. So polyatomic. So poly means many. So if you look at these, you're going to see multiple atoms. You're going to see hydrogen. So like right here, you're going to see hydrogen, carbon, and oxygen together. So that is a polyatomic. Okay, so let's go back up to here. So polyatomic ion. Okay, so an example would be something like nitrate, which would be NO3 with a -1, or carbonate, which is CO3 with a -2. Okay, so that's a polyatomic. Oxidation is a fancy word just for the charge. Okay, so a lot of people ask what the oxidation number is. It is just the charge. Okay, so that could be like a +1, a -3, just the charge. Okay, so transition metals. So remember, transition metals are in that D group. Okay, so let's go back to that periodic table since a lot of people get confused on the transition metals. So we're going to touch base on that one more time. Okay, so transition metals start right here in group 3 and go to the right to the staircase. Okay, except for silver, which is +1, zinc is +2, and aluminum is +3. Everything else needs a Roman numeral. Okay, so that means they have more than one charge. Okay, so that is why we use Roman numerals to tell us what the charge is. Okay, so if I did copper with a Roman numeral of 2, that means it is going to be copper, so Cu with a +2 charge. Okay, because copper could be anything. It could be +3, could be +1, but that particular one is +2. Okay, describe the properties of ionic compounds. Okay, so this was a question in the last test that some people kind of messed up on. So this one is just kind of one of those things you just kind of have to know and kind of put that in your memory. Okay, first thing is it creates a crystal lattice. Lattice is just a repeating crystalline structure. Okay, so it just kind of looks like a crystal. Okay, they're going to have high, let me fix that. High melting points and boiling points. Okay, because ionic bonds are very strong. Okay, so they are very strong bonds. That's when you take a metal and a non-metal. Okay, so if it's a strong bond, it's going to take a lot of energy to break that up. Okay, so they are non-conductors as solids. Let me fix that. So they are non-conductors as solids. Okay, so not very good for heat or electricity. Okay, they are soluble in water, so it means they can break apart in water. Okay, which then, once they're broken down into water, then they become good conductors. So they have to be dissolved first to become good conductors. Okay, so that's where you get terms like electrolytes. Okay, and they are very hard and brittle. Okay, so this is just kind of those things you just kind of put in your memory bank. Okay, so now let's jump back across here. So I already did number 42 since I jumped ahead on accident earlier. Now we're going to go into writing the ions and chemical formulas for the ionic compounds. Okay, so we're going to start off with barium chloride. So the first thing I'm going to do is I'm just going to write out each thing. So this is where you're going to need your periodic table. Okay, so if you want to get yours ready, so that way I'm not scrolling back and forth all the time. Okay, so barium is going to be Ba, so it's in group 2 with a +2 charge. Okay, chlorine is on that group 7, that's going to be a -1 charge. Okay, so I can see right now that these are not balanced, so what I'm going to do is I'm going to do the crisscross method. Okay, so that means I only need 1 barium, and I need 2 chlorines. Okay, so now it is balanced. So that means I have a +2 charge on the right side, and then since I have 2 chlorines, that means there's a total of -2 on the right side, so that means I'm perfectly balanced. B, potassium is K with a +1 charge, and nitrogen is going to be N with a -3. I can tell right now this is not balanced. Okay, give me a second. I don't know why this is jumping all around. Okay, so that means I can do the crisscross method, so I'm going to take that 3 here, take that 1 there. Okay, so this is going to be K3N. So now it is balanced. C, I'm going to do magnesium iodide, so Mg with a +2. Iodine has a charge of -1. This is not balanced, so I'm going to do the crisscross method. Okay, so that means I only need 1 Mg, but I'm going to need 2 iodines. Aluminum phosphide, so I'm going to do this one, so Al with a +3. Okay, phosphorus is going to be P with a -3 charge. Okay, if they're already balanced, you do not need anything more. So you would just put them together. This would just be ALP. So you don't have to do the crisscross method if they're already balanced. So there's no point in doing that. So it'd just be ALP. Okay, cesium has a +1 charge. Fluorine has a -1 charge. Okay, so they're already balanced, so I don't need to do crisscross or anything. So this would just be CS and F. Okay, so hopefully that kind of helped out with that. So let's jump down to number 44, so I'll make sure not to do that mistake again. Name the following compounds. Okay, so this is going to be a little easier. You don't have to worry about really breaking it apart. Okay, so magnesium, that is going to be in group 2. So I will say before we do naming, it is good to check to make sure that your cation is not a transition metal. Okay, so if we go over here to our periodic table, if it is in, let me do a different color. If it is in this group, these 2 groups right here, you do not need a need a Roman numeral. Okay, so since they do not change, Okay, you do not need a Roman numeral. Roman numerals are only needed for transition metals except for silver, zinc, and aluminum. Okay, anions, you don't need a Roman numeral for an anion either because these never change. Okay, so these always have that same charge. So you don't need a Roman numeral for anions. So we only use it for transition metals except for silver, zinc, and aluminum. Okay, so now let's go back to that. Okay, magnesium. So Mg is magnesium. Okay, and chlorine, so that is now chloride. Okay, so remember, if it's just chlorine by itself, it's going to end in IDE. Okay, and magnesium is not a transition metal, so that is in group 2, so it's not a transition metal, so we do not need a Roman numeral. Okay, calcium, that is not a transition metal, so we're just going to write out calcium. And then phosphorus becomes phosphide. Okay, Al2O3. Okay, so Al is aluminum. So even though aluminum is in that group of transition metals, remember it has a charge of +3 always, so you do not need a Roman numeral for it since it does not change. So this is just aluminum oxide. Okay, so there's a few examples on how to do that one. Okay, so those are pretty simple. Number 45, write the ions and chemical formulas for the following compounds. Okay, so manganese 7. Okay, you have to really be careful with manganese. We see a lot of confusion between manganese and magnesium. Okay, manganese is Mn. Okay. Let's go to the periodic table on that because I don't want y'all to miss points on that just because you get confused on magnesium versus manganese. So let me clear this up real quick. Let me just kind of tidy this up. Okay, so you have to really be careful with this because magnesium is right here and manganese is right here. Manganese is a transition metal and it does need a Roman numeral. Okay, now let's go back up here. So manganese, this right here tells me the charge of manganese since it's a transition metal. So VII is going to be 7. Okay, if you need a brief refresher on Roman numerals, 1 is going to be I, 2 is II, 3 is III, 4 is IV, 5 is V, VI is 6, and VII is 7. That's all you have to know. So we have manganese with a +7, and you have oxygen, which is a -2. Okay, so if it helps, you can always start with your oxygen. You can always start with your anion, okay, because the anions don't ever change. So right now I can see that these are not balanced. So what I'm going to do is I'm going to do the crisscross. Okay, so that means I would need 2 manganeses and 7 oxygens to be balanced. So that would be my answer. Okay, let's do iron 3 sulfide. So iron is Fe. So that iron 3 tells me the charge. So this is a +3. So it tells me the charge, not how many. Okay, and then sulfur is going to be a -2 charge. Okay, so this is going to be S with a -2. I can tell that these are not balanced, so I'm going to do the crisscross. So that means I need 2 irons, so Fe2. Let me fix that. So this would be Fe2, and I need 3 sulfur, so S3. And that would be my answer. Let's do another one. So copper 2 chloride. So copper is Cu. Okay, and that 2 tells me I have a charge of +2. Chlorine has a charge of -1. Okay, so it is not balanced, so you can do the crisscross. So that means I only need 1 copper, and I need 2 chlorines. So that would be my answer right there. And we'll just do one last one for good practice. So titanium is Ti with a +3 charge, so they told me Ti3. And then phosphorus is going to be P with a -3 charge. So they're already balanced, so you don't need to do crisscross, so this would just be TiP. Okay, number 46. So now what we're going to do is we're going to kind of go backwards now. So I'm going to jump to B since A we already kind of did in the last problem. Okay, so what you're going to do is we're going to split these up. Okay, so we need to find the charge of your transition metal. Okay, so I'm going to do Cu and then F. Okay, so the way I do this is I always start with the anion. Fluorine always has a charge of -1. Oh, sorry, I wrote a 2 there. Don't know why. Fluorine has a charge of -1. Okay, and since I have 2 of them, okay, so I have 2 fluorines, meaning my total charge, so -1 times 2. Jesus, I cannot write today, so let me go ahead and just start that over. Okay, so I have Cu. Okay, and then I have F. So I'm looking for this charge right here, and I know F has a charge of -1. I don't know why I cannot write, sorry. -1. Okay, so now what we're going to do is I have 2 fluorines. So that if I have 2 fluorines, that's times 2. That means I have a total charge of -2 for my right side. That means this side has to be a +2. Okay, to be balanced out. Okay, so if my left side, my copper, has to be a total of +2, okay, I'm just going to divide it by however many coppers I have. Okay, I only have 1. So that means the charge of copper would just be +2. So if I were to write the name of this would be copper 2 fluoride. Okay, so let's do another example. Let's jump over here to PbCl4. Okay, so Pb is lead, so I don't know the charge of it, and I need that for my name. And chlorine, we know always has a charge of -1. Okay, I have 4 of them, so -1 times 4 equals -4. So that means my total charge for my anion is a -4, meaning my left side has to be a total of +4 to be balanced. Then I'm just going to divide that by however many I have. Okay, so I'm going to take that 4 and divide it by, I only have 1 lead, so 4 divided by 1 equals +4. Okay, so this would be lead 4, so this is IV chloride. Okay, so I can show you another example on how to do this. So if this works better for you, that's great. If it confuses you, don't worry about it. Just do whatever feels best for you. Okay, so remember we did oxidation numbers. Okay, so the way we did this, the way I did it was, first thing I'm going to do is I'm going to split them apart. Okay, I'm going to see that there is no charge here. So what I'm going to do is I'm going to take my total charge and set it equal to 0. Okay, so if there's no charge, I'm going to set it equal to 0. Okay, I'm always going to start with my anion first. Okay, so I'm going to start with oxygen. Oxygen always has a charge of -2. So 3 times -2 gives me -6. So I would see what -6 gives me 0. So this would be 6, a +6. Okay, and so since my total positive charge has to be 6, and I only have 1 chromium, if you take that 6 and divide it by 1, that means this chromium has to have a charge of +6. So the name of it would be chromium 6, so Vi, and this is oxide. Okay, so if you want to see me do that again, okay, so let's go down here to H. Okay, I'm going to split them apart, Ag2S. Okay, there's no charge here, so that means I'm going to set my total charge out equal to 0. I'm going to start with my anion, so sulfur has a charge of -2. There's only 1 of them, so 1 times -2 is -2. So I need to see what -2 equals 0. So this would have to be a +2. Okay, so now I have 2 silvers. So I'm going to take this total of a +2 and divide it by however many I have. So 2 divided by 2 equals 1. So that means each silver is going to have a charge of +1. Okay, so this would just be silver 1 sulfide. Okay, so I can do one more example of that because I know that may be new to you, so I can show you again on how to do that. So I have Zn3, so let's try this one. Zn3, I'm going to separate them. Okay, so I'm going to give myself some room. Okay, there's no charge here, so that means I'm going to set my total out to 0. Okay, I'm going to start with my anion because phosphorus is always going to be a -3. So 2 times -3 is -6. So what -6 equals 0? So 6 minus 6 equals 0. but I have 3 zincs. So I'm going to take that 6, so 6 divided by 3 equals plus 2. So that means each zinc is going to have a charge of plus 2. Okay, so so I just showed you how we got the charge of zinc, even though on the periodic table we always know zinc is a charge of plus 2. Okay, so remember it's one of those 3 exceptions. Okay, so this would be zinc phosphide. So since it does not have a differing charge, zinc's always going to be plus 2. We do not need a Roman numeral, which brings me back over to H. I made a mistake there because I got in the zone of finding the transition metal. Okay, and I didn't even realize that silver was always plus 1. So I do not need this 1 right here. So that was my mistake because I kind of got in the zone of finding that transition metal. Okay, so remember, your exceptions are silver is always plus 1. Okay, zinc is always plus 2. And then aluminum is always plus 3. So these do not need Roman numerals. Okay, so that shows that even I can make mistakes on this. Okay, because you just kind of get in that zone. Okay, so we're going to go over here now to number 47. Write the ions and chemical formulas and the following ionic compounds. Okay, so if you notice, you're starting to see things like 8s. Okay, or you see like hydroxide or acetate. Okay, so instead of you trying to look all over the periodic table for these, okay, I would have this list handy. This polyatomic list right here. You get this on the exam. Okay, so I would take a look at this before the exam so you kind of know what's on it, so you're not trying to look on the periodic table for something that's not there when it's on this list. Okay, so let's go back up to here. Okay, so sodium chromate. Okay, so first thing I'm going to do is we're going to write ions and the chemical formula. So first of all, sodium is going to be Na with a plus 1. Chromate, if you look up chromate on that list, is going to be CrO4 with a minus 2. So if you want to, we can go back to that list. So chromate is right here. Okay, so CrO4 with a minus 2. Okay, I can tell it's not balanced. So you can still do the crisscross method. So I can take this 2, bring it over here, take this 1, bring it over here. So that means I need 2 sodiums and only 1 chromate. Okay, so next one, barium nitrate. Okay, so barium nitrate. So Ba with a plus 2. NO3 nitrate is NO3 with a minus 1 charge. I can see that it's not balanced, so I can do my crisscross. So I only need 1 barium, but I need 2 nitrates. So what you're going to do is you're going to put nitrate all in parentheses. Okay, because you cannot touch that at all. So you cannot touch that 3. You cannot do anything like that. So I'm going to put it in parentheses, and I need 2 of them. So that would be my answer right there. Okay, C, ammonium sulfate. So ammonium is on that polyatomic list too. So that is NH4 with a plus 1 charge. Sulfate is also on that list. Okay, so that's going to be SO4 with a minus 2. Okay, I can see that that is not balanced. So you can do the crisscross. I could take that 2 over to the NH4, so that means I need 2 of them. So I'm going to put the whole thing in parentheses with a 2. And only need 1 sulfate, so I'm going to leave that as SO4. Okay, so let's do some of these transition metal ones. Okay, so F, copper 2 sulfate, so that means we have Cu with a plus 2 charge. Sulfate is SO4 with a minus 2. It's balanced, so all you got to do is put them together. So CuSO4. Iron 2 nitrite. Okay, so Fe is iron with a plus 2 charge. Nitrite is NO2 with a minus 1 charge. Okay, it's not balanced. You can do the crisscross. So that means I only need 1 Fe. But I need 2 nitrites. So I'm going to put the whole thing in parentheses. NO2 and then 2. Okay, let's do one more. So tin, 4. So tin is SN. That IV tells me it's a charge of plus 4. Acetate is also on your polyatomic list. That is C2H3O2 with a minus 1 charge. It is not balanced, so you can go ahead and do the crisscross method. So I only need 1 SN. but I need 4 of these acetates. So I'm going to put the whole thing in parentheses. So C2H3O2, and I need 4 of them. Okay, so I'm going to put that 4 outside of it right there. Okay, the big thing you need to know is that usually when you deal with things like ide, okay, that is when you're dealing with monoatomic. Okay, so if I did this, NaCl, okay, this would be sodium chloride. Okay, if it ends in ate or ite, okay, that is going to be on that polyatomic list. Okay, so that would be something like this. So this would be NaClO3. That is going to be sodium chlorate. Okay, so just watch out for your suffixes there. So ide, okay, ide usually means it's just the element by itself, so it means it's just chlorine by itself. Okay, chlorate or chlorite, that means you're dealing with a whole polyatomic now. Okay, so it's not just one element. So let's do some naming practice. Name the following ionic compounds. Okay, so NH4 is on your polyatomic list. This is just simply ammonium. Okay, and chlorine, so since it's just chlorine by itself, this would just be chloride. K2Cr2O7. Okay, so K2 is potassium. Okay, it is not a transition metal, so we do not need a Roman numeral in our name at all. Okay, and Cr2O7 is just on that polyatomic list. That is dichromate. BeSO4, so Be is beryllium. Okay, and SO4 is on your list, on your polyatomic list, that is sulfate. Okay, so let's do some of the actual transition metal ones. Okay, so on F right here, I have Cu2SO4. Okay, so we need to find the charge of that copper. Okay, so if I split these up, so even though I'm not going to do this one or this one, so I'm just going to write this up here. Cu2 and SO4. Okay, SO4, if you look up that on your polyatomic list, that has a charge of -2. That means this whole left side has to be a charge of +2 to be balanced. But I have 2 coppers. Okay, so I'm going to take that +2 and divide it by however many I have, meaning each copper has a charge of +1. So when I write out this name, it's going to be copper 1 sulfate. Okay, so let's do another one. So I have Pb3, and I have 4 PO4s. Okay, so there's multiple ways you can kind of do this. You can do a reverse crisscross method. I can take the 4 up to the top left. I can take the 3 up to the top right. That only works if when you take that charge up to the anion, if it matches the charge that's either on the periodic table or on your polyatomic list. Okay, so I'm going to do it both ways, just kind of show you. So if I did this, take this 3 up here. Okay, that means PO4 has a charge of -3. And then and I'm going to bring this 4 up here. So PB has a charge of +4. Okay, so I would look on my list. So I need to look on my list and see if PO4 has a charge of -3. If it does, it works. Okay, so phosphate has a charge of -3, so that reverse crisscross would work. Okay, the reason why sometimes it doesn't work, because remember, if it can be reduced, it will be. Okay, so sometimes that's why the reverse crisscross doesn't work. So I usually check the anion, and if I do the reverse crisscross, and it matches the charge of the anion, then you're good. So that means this would just be lead, so Pb is lead, 4 phosphate. Okay, so let me show you the other way. Okay, so if I went back, and let me clear up this a little bit more. PO4 has a charge of -3. If you looked up in the list, that's -3. But I have 4 of them, so 3 times -3 times 4 equals -12. So that's my total negative charge on the right side, meaning my left side would have to be a +12. Okay, but I have 3 lead, so 12 divided by 3 equals +4. Okay, so there's multiple ways you can do that. Whichever way works for you is best. Okay, so that's just kind of to help you there. Okay, on this list, so I've done enough practice on all of these to kind of help you out with that. So the list is just the same thing. It's just more practice for you, so you can kind of check the key on that. You can also let us know if you have any questions on that. So if you need help with this stuff, I would honestly go back to this part so you can rewind and kind of see how I do it, because I pretty much went through every possible way. Okay, if we gave you ions, so your cation and anion, and we asked you to put them together and tell me the name, or if I gave you the formula, how to break them apart, okay, or if I gave you the name, how to break it apart, okay, and how to balance, so that's all kind of there. Okay, so let's see what we have left. Okay, lastly is just going to be oxidation numbers. So we're almost there. Okay, so oxidation numbers just means we're trying to find the charge of each thing. Okay, when it's something by itself, okay, so Cl2, okay, there's no charge here. So that means the oxidation number for chlorine is just 0. Okay, so carbon, there's no charge here, so that means carbon equals 0. So those are kind of gimmies. So now, I'm going to start off with something kind of simple. So I'm going to kind of write them down here to give me some more room. So I'm going to do letter C, so H2SO3. And the way I do this is I just kind of write this out. I spread them out. So H2SO3. Okay, I'm going to draw my total line. There is no charge up here on this. Okay, so that's what I'm going to set my total to, is 0. Okay, so oxygen, you always start with your oxygen. Okay, that is the easiest way to do this. Oxygen always has a charge of -2. So 3 times -2 is -6. Okay, I'm going to save this one for last. Okay, so do not look up sulfur on the periodic table and tell me what the charge is, because since it's bonded with oxygen, it will be different. So what I'm going to do is I'm going to go over to hydrogen. So I did oxygen first, so that's step 1. I'm going to do my metal, or in this case it's just hydrogen, that's step 2. And I'm going to save sulfur for last, which is step 3. Okay, so hydrogen always has a charge of +1, but I have 2 of them. So 2 times +1 is going to give me 2. So 2 plus blank minus 6 equals 0. So now I'm trying to find the sulfur's charge. Okay, so I know my total charge for sulfur has to be 4. Okay, and since I have only 1 sulfur, so 4 divided by 1 is just going to give me 4. So that means the charge for sulfur is going to be +4. Okay, so my answer would simply be H equals +1, S equals +4, and then oxygen equals -2. Okay, so let's do I did this one, so let's do this letter C. I don't know why we have 2 C's. Okay, so I'm going to split it up. So Mg3. Okay, watch out for parentheses right here, because this 2 carries over, so that means I have 2 arsenics. So As2. And then I have 4 oxygens on the inside of the parentheses, so 2 times 4 is going to be 8. So this is going to be O with an 8. Okay, so I can see that there is no charge up here, so I'm going to set that equal to 0. Okay, so I'm going to do my total line. I'm going to set it equal to 0. Okay, I'm going to do oxygen first. That's my first step. Okay, oxygen always has a charge of -2. So 8 times -2 is going to give me -16. Then I'm going to go over here to my metal. I'm going to save the arsenic for last. Okay, so this is going to be my step 2. So let me fix that. So step 2. Okay, so Mg always going to have a charge of +2. Okay, and I have 3 of them. Okay, so 3 times +2 is going to give me 6, so +6. So now I can find arsenic. So 6 plus blank minus 16 equals 0. Okay, so 6 plus 10 minus 16 equals 0. So that means my total charge for arsenic has to be 10. But I have 2 of them. So 10 divided by 2 equals +5. So that means each one's going to have a charge of +5. So my answer would just be Mg equals +2, arsenic equals +5, and oxygen equals -2. Okay, we can kind of do another one just for a real quick example. So let's do Al2S3. So Al2S3. Okay, so you can say this is a good way to help find the charge of something if you're not sure. So that's why I kind of showed that step earlier. Okay, so Al2S3, There's no charge up here, so I'm going to set equal to 0. Okay, I'm going to start with my anion always first. Sulfur has a charge of -2, so -2. 3 times -2 gives me -6. So what -6 gives me 0? So 6 minus 6 gives me 0. So that means my total charge for aluminum has to be +6. But I have 2 of them. So 6 divided by 2 equals +3. So that means my aluminum has a charge of +3. So my answer would be Al equals +3 and S equals -2. Okay, so that's how to do the oxidation number. So there's probably going to be just a couple of those on the exam. Okay, but that also helps figure out the charge of something. So I honestly, for this one, I didn't even need to really do that if you can look on the periodic table. Okay, because I know sulfur is always -2 and aluminum is always +3. But if you're having questions on how to find the charge of something, so this step would be really good to find the charge of a transition metal. Okay, so if you have any questions, just let us know. Hopefully that kind of helped out. So kind of rewind if you need anything else. And then just if you need help with any other parts or any other things that you need more in-depth explanations, you can go back to some of my old reviews and get some more help there. So hope that helped. Let us know if you need anything.